Hello everyone. Thank you for joining this session. Today we are going to discuss about eye diagrams for high-speed digital designs. I want to walk you through the basics of eye diagrams, what they are, how we use them in the signal integrity analysis, and how to read and improve them. And in this session we are going to discuss about the basics of eye diagrams when it comes to signal integrity analysis and how to interpret and improve the eye closures. Let's get started. First of all, we are going to discuss about what is an eye diagram with respect to high-speed digital designs. So an eye diagram is basically a way to visualize how clean or noisy a high-speed digital signal is. What we do is overlapping multiple cycles of signal, kind of stacking them, and that forms a pattern that looks like an eye. As you can see in this diagram on the right, there are two eyes that I have mentioned. One is a completely open eye and the second one has some sort of issues with respect to signal integrity. The shape of the eye and openness of this eye tells us a lot about how good our signal is. If the eye is wide open and clear, that's a good sign for signal integrity. But if it's messy and closed, we have to focus on our time domain analysis when it comes to signal integrity analysis. Now let us quickly discuss about the construction of an eye diagram. How do we actually make an eye diagram? It's a simple concept. We take repeated bits of a signal and align them over time and see them from the top view. Think think of it as a stacking of a lot of waveforms on top of each other and then looking at them from the top view. This overlapping helps highlighting variations in signal transitions such as jitter and noise. And once you see this eye forming, you can quickly tell how reliable your signal might be. As you can see on the left side, we have four waveforms and we have overlapped each of them on each other and we have created these eye diagrams over here. Let's break down the anatomy of an eye diagram in high-speed digital designs. In case of high-speed digital designs, eye diagram is being analyzed in four different methods. One is eye opening, second is the crossing points, then comes the jitter and noise margin, and then comes the mask testing region. Let's discuss about these points separately. First is eye opening. Eye opening represents the signal integrity. A wider opening indicates low noise and jitter and ensures reliable data transmission. The yellow area that you are able to see in this eye diagram is nothing but the eye opening. Then comes the crossing points. Crossing points are where the signal transition occurs. The consistency of crossing points reflects the clock stability and timing accuracy. As you can see over here, these are considered as the crossing points. Then comes the jitter and noise margin. The horizontal variation that you are seeing over here is considered to be the jitter, and the vertical distortion that you are seeing over there is considered to be the noise. Jitter impacts the signal timing, and when it comes to vertical distortion, that is noise, it impacts the amplitude. The, the last and foremost part is mask testing region. Mask testing region defines the industrial standard limits, and any signal crossing into this region indicates a potential in transmission errors. The signal loss occurs whenever a mask is being violated. And when it comes to measurement in eye diagram, there are different parts that we usually measure. First is the eye height, then comes the eye width, then comes the unit interval and the amount of jitter. So in a nutshell, eye diagram in high speed digital designs provide us the detail about your timing error as well as your noise level errors. Now let us understand what you can learn from an eye diagram. On the right side, you can see an eye diagram that has a high height, eye amplitude, rise and fall time, eye width, amplitude of the jitter, and zero crossing time jitter points. There are majorly four categories of things that you can see when you see an eye diagram. First is the timing jitter. The timing jitter includes both random noise and the timing skews when it comes to a differential pair. Then comes the signal level variance. When I say signal level variance, I usually talk about the amplitude part, and this can be distorted by impedance mismatch or some sort of random noise in the signal. Then comes the average rise and fall time. When a signal is on its rising edge, the signal between 10% to 90% of the signal is considered to be the rise time. And this kind of signal is influenced by channel response, noise, reflections, and ISI. ISI stands for inter-symbol interference. Then comes the bit error rate. The bit error rate tells us how often we might misread a bit. Tools like equalization and pre-emphasis can help us clean that up. In case you are working on a high-speed signal, the bit error rate gives you the data about how many bits are going to get lost during the whole transmission. The ideal bit error rate can be between 10 raised to the power minus 12 or lower than that. And in case if you want to reduce the bit error rate, equalization techniques can be used either at the transmitter or at the receiver end. If you want, I can create a separate video on equalization. Please comment down below. Till now, we have seen the basics of eye diagram. Now let us see how an eye diagram can help in signal integrity analysis. Eye diagram is a powerful tool in signal integrity analysis as they give us a quick visual check for signal integrity quality. You can use them to spot where timing is off, where voltage levels are varying, or where there is a noise in the crosstalk. It really helps us debug designs at the earliest phase before we build an actual hardware. Now let us discuss each of these points in detail. The first is the measurement of timing jitter, voltage noise, and signal distortion. An eye diagram gives you an idea about the timing jitter, whether it's a deterministic or a non-deterministic, or we call it as a random jitter, the voltage noise, and whatever the signal distortion in terms of crosstalk or in terms of impedance mismatch is happening in your signal. Then comes the evaluation of signal to noise ratio and the intersymbol interference. Intersymbol interference and signal to noise ratio plays a major role when it comes to the high speed digital signals, where between two signals, if there is an overlap of signal, then you are going to see a closer eye. That means you are having some sort of timing errors or you are having some sort of signal integrity errors. As we discussed earlier, this eye diagram can help you to check the impact of channel loss such as reflections and crosstalk. And the last point is that this eye diagram ensures the compliance with the standards like PCI, USB, Ethernet, DDR with the help of eye mask inside it. So all these four points gives you a better idea about how eye diagram can help a signal integrity analysis. Now let me take you through few of the common eye diagram issues. The first one is the narrow eye opening. This narrow eye opening indicates the excessive jitter or noise. Jitter in the time domain and noise in the amplitude domain. Then comes the increased intersymbol interference. Intersymbol interference distorts the eye due to signal reflection. Then comes the reduced eye height. If you are seeing a lower high eye height, that is because of the noise based on crosstalk and the signal reflection. And then comes the asymmetrical eye pattern. Asymmetrical eye pattern creates when there is an imbalance between your rise or fall times affecting the time diagram or the timing margins. Recognizing these patterns helps us figure out what to tweak in the major design phase. Now let us see the methods to improve the eye closure. If you see a bad eye diagram, don't worry. There are ways to fix it. You can use equalization, pre-emphasis, and improve your layout or control your impedance better or reduce crosstalk. A lot of times it's about balancing these things. The goal is to open an eye as much as possible. Now let us see few of the points or few of the methods to improve the eye closure. First is by reducing the jitter. This can be done by using a low jitter clock source or by optimizing your PCB routing to reduce the reflections in the signal. Then comes by improving the signal integrity. When we say improving the signal integrity, we talk about the impedance discontinuities throughout from your transmitter to receiver. It may happen at the trace level or at the via levels or when the signal is traveling from board 1 to board 2 through some sort of connectors. Then eye diagram can also be improved by looking at your power integrity analysis. An improved power delivery network can help you implement proper power integrity practices. You can use decoupling capacitors for power stabilization. Then comes the equalization techniques. When I say equalization techniques can be used at a transmitter as well as receiver. At transmitter, we have three type of equalization techniques that we use. One is pre-emphasis, then comes the de-emphasis, then comes the FFE. FFE stands for feed forward equalization. Then comes at the receiver end. There also we have three categories of equalization that can be used. One is FFE. FFE stands for feed forward equalization. Then comes the DFE. DFE stands for decision feedback equalization. Then comes CTLE. CTLE stands for continuous time linear equalization. As you can see, FFE can be implemented at the transmitter as well as at the receiver end. So by focusing on these area in your design phase, you can improve your eye closure and you can get a better understanding on eye opening. Let me conclude my slide with three major points. First is eye diagram is considered to be a most crucial tool for analyzing a high-speed digital signal. Then comes a well-opened eye ensures the robust data transmission with minimal errors. And if your eye is a closed eye, then there are issues such as crosstalk, impedance, jitter, timing errors, as well as the amplitude based errors. Then SI techniques such as jitter reduction, impedance control, and equalization improve signal quality, and that can help you to understand more into your signal integrity and power integrity based issues. That's all from my side. Thanks a lot for your time. I hope this gave you a good overview of eye diagrams and how they fit into signal integrity works. You can always connect with me through my LinkedIn profile through the scanner available. Please feel free to comment down your questions and subscribe to my channel. Thank you and have a nice day.